In this video, I'm going to take the concepts of average kinetic energy that we looked at throughout this unit and apply it to state changes and intermolecular forces, which are concepts that we previously studied. But before I actually get started, what I want you to do is I want you to look at the first section, the evaporation in open systems, and I want you to answer those questions because those questions come from your daily experiences, not necessarily just chemistry. So please look at that and then I'll go through and I'll explain them. Alright, so the first thing asks us to look at a puddle and consider a puddle. And what happens to that puddle if we leave it undisturbed? Well, obviously we know that water is going to evaporate. The way that we can actually make this process, the process of evaporation, go faster is if we increase the temperature of the solution. Well, that's kind of common sense to us, but in a chemistry point of view, why exactly does increasing the temperature of a solution facilitate evaporation or increase the rate of evaporation? And so if you look at this graph, it actually helps us to understand the relationship between temperature, kinetic energy, and then the number of molecules that are being able to evaporate. So there is a minimum kinetic energy that molecules must have in order for them to transition from being a liquid to a gas. Now, the reason why there's a minimum kinetic energy is that otherwise molecules are going to hold on to one another through intermolecular attractions. And so if they're holding on to one another, they're not going to become gases. So there must be a minimum kinetic energy, a minimum energy that they're moving with in order to counteract these intermolecular attractions. So if they reach this kinetic energy, this minimum kinetic energy, what this graph then notes is that more molecules that are at a higher temperature are able to reach this minimum kinetic energy than are molecules at a lower temperature. And so that explains why when we have a liquid that we're trying to evaporate, why a higher temperature makes it easier for it to evaporate, because that means you're going to have more molecules with the minimum kinetic energy that enables them then to leave and become gases because they are able to overcome the intermolecular attractions between molecules. Now, the next question is actually interesting, and this explains why you sweat. It asks what happens to the temperature of the remaining liquid after those molecules have evaporated. And what actually happens is that temperature decreases. And the reason why is because you are losing molecules that have a high enough kinetic energy to leave the solution, and therefore the molecules that are left have a lower kinetic energy and therefore a lower temperature. So that's why you sweat, why when your sweat evaporates, that leaves you with cooler liquid on your skin, and therefore it's an attempt by your body to cool your body. So let's talk about evaporation in a closed system. So a closed system simply means that it's closed off from the atmosphere. And what you should notice in the diagram on the right-hand side is once molecules have been allowed to evaporate, it reaches the point at which molecules are leaving and going from the liquid form to the gaseous form at the same rate as gases are becoming liquids again. And so this is called dynamic equilibrium. We'll look at dynamic equilibrium a lot in the equilibrium unit for this class. However, it's important for you to know that it's a condition in which two opposing processes occur at the same rate. So the state change from liquid to gas is occurring at the same rate as gas to liquid. Now, we might not be able to see a difference because it seems like the amount of gas and the amount of liquid staying the same, but you still have this transformation of liquid to a gas and then a gas to a liquid. They're just occurring at the same rate, so it seems like nothing is happening. So that's why we call it dynamic equilibrium. Another term for you to note is this concept of vapor pressure. Vapor pressure is the pressure exerted by a vapor in the space above the liquid. So if you look at this diagram above with those arrows, that pressure that those gaseous molecules exert, that is the vapor pressure. The last concept that I want you to be familiar with is this idea of volatility. And the volatility is the ease with which liquids evaporate. So the easier it is for a liquid to evaporate, the more volatile it is. So for example, alcohols are extremely volatile. And what we'll notice is the fact that alcohols are extremely volatile because they have weaker intermolecular forces than, let's say, water, which is not volatile. So let's look at vapor pressure and consider how intermolecular forces affect vapor pressure. If you look at all of these different substances, the vapor pressure of diethyl ether is much higher than that of ethyl alcohol, which is higher than water, which is higher than ethylene glycol. And what you should notice is diethyl ether is actually a nonpolar molecule and therefore has dispersion forces, while ethyl alcohol, water, and ethylene glycol have varying degrees of hydrogen bonding. So ethylene glycol is the strongest with the strongest hydrogen bonding. Therefore, the molecules of ethylene glycol are going to hold on to one another much tighter than diethyl ether, and as a result, you're going to have fewer ethylene glycol molecules that are in the gas form. Therefore, the vapor pressure of ethylene glycol is going to be a lot less. So let's see how vapor pressure affects boiling point, which is a characteristic that we've already looked at, but let's look at it again. When vapor pressure equals the atmospheric pressure that's acting on the surface of a liquid, that's when boiling occurs. And so the boiling point of a liquid is the point at which it boils, the temperature at which it boils, when it's under 1 atmosphere of pressure. Now there are a couple of important points for you to know. The lower your atmospheric pressure, the lower the temperature at which a liquid will boil, and that's because your vapor pressure just has to equal the atmospheric pressure. So if I'm up high on a mountain, the water that I'm trying to boil for dinner is going to boil at a lower temperature. Now that sounds like a good thing, but actually, if I'm trying to cook pasta, I want it to reach the maximum temperature it can reach before it starts to transition from a liquid to a gas. So normal water boils at 100 degrees. Well, if I'm on a mountain and the water starts to boil at, let's say, 95 degrees, that will cook the pasta slower. One technique that's actually used in the kitchen to take advantage of this fact is a pressure cooker. And so what happens in a pressure cooker is you are able to increase the pressure within the pressure cooker beyond that of the atmospheric pressure. Therefore, that allows the water to boil at a much higher temperature because it requires more heat to get it to boil. Therefore, let's say it's boiling at 110 degrees. That enables the pasta to cook even faster. So that's one technique that's used in the kitchen. Now, if vapor pressure is extremely high because the intermolecular forces that are attracting molecules are very weak, then that means that that substance is going to boil at a much lower temperature. And that's simply because less heat is required in order to get the vapor pressure high enough so that it's equal to the atmospheric pressure. So if you're trying to boil water versus trying to boil an alcohol, the boiling point of an alcohol is going to be much lower than that of water because the alcohol has a much higher vapor pressure because it's volatile, because it's much easier for it to move from a liquid to a gas than water.